Thanks.
It's sort of amusing in a way that Rick should get stuck with the last paper of the morning.
Why is that? I'd like to spend just a few minutes raising some questions and pointing out a possible topic for discussion that I think will come up later on in the hot-cold particle session, which tends more to deal with the interactions between the two major particle populations. In keeping with the spirit of the meeting, I would like to at least suggest some possible effects that the hot particles might have on the cold particles. The effect of the plasmasphere on the ring current in terms of pitch angle diffusion and loss of ring current protons has been widely discussed, but let's look at the possible effects of the ring current or plasma sheet or alphane layer or hot particle boundary, however you want to refer to it, on the motion of the cold plasma. The first slide shows the old teardrop approach. This is where you just assume there's a convection electric field driving the cold plasma and a co-rotation field, and it has no effects of the hot particles in it. We found in the past that this defines or will give you the dynamics of the plasmasphere and the general morphology of the plasmasphere reasonably well. It gives you the bulge in the right place. It gives you the expansion in the bulge region, which causes the decrease in the density profiles, roughly 1 over L to the 4th that's observed there. If you vary the convection field, you can find that you get a compression of the plasmasphere on the night side in enhanced convection times. You get an expansion of the plasmasphere generally on the night side during decreasing convection electric field times. Also, during enhanced convections, when you go from a quiet situation with a large plasmasphere to a more active situation, there tends to be a detachment or the development of a tail in the dusk sector, general loss of plasma from the plasmasphere, which causes a shrinkage in the size of the plasmasphere. The overall teardrop model seems to be very good for these features. However, there are a lot of characteristics of the plasmasphere which are very perplexing to try to understand in terms of this model. For example, there's the question of whether the plasma loss from the plasmasphere in the afternoon sector is actually a detachment or whether it is a slow evolution of a tail and loss of plasma in that way. In order to get detachment, you have to have very large gradients in the electric fields, spatial gradients, to cause a differential type flow. If you have a smooth convection field, then you would have the development just of a long tail. Another body of data which is very hard to understand in terms of just the teardrop model is the body of data that's coming out of the Chattanooga radar, where you see very large changes, they are apparently spatial changes when you look at them on a daily or say dawn to dusk type scale, one case right after another. Very large changes in the electric field, apparently large gradients in the electric field, and very large magnitudes in the flow. You can't get large gradients like this in the electric field from the teardrop model, and it leads you to say, well, what else could be causing effects here that are going to impact on the drift of the cold plasma? And I think the first obvious one to go after, which was suggested, I think, originally by Carlson and then followed up by Vasiliunas and Wolf, and subsequently Yagi and Wolf have actually developed a computer model to simulate the effect, is the inclusion of the hot particles and the beginning to look at what effects they might have in shielding off the convection field from the plasmasphere. How does that impact on the dynamics of the plasmasphere? And first thing we'd want to show is where does this hot particle boundary, or let's just call it hot particle boundary. In the dusk sector, it's primarily the ring current around to midnight, and then it's more the plasma sheet from midnight on around toward dawn. Where is it really there, and where is it generally? There's a set of observations from Frank on LGO 3 that show that the electron plasma sheet is generally very close to the plasma pause position in the midnight sector on toward dawn, and that in pre-midnight the ring current is adjacent to or overlaps the plasma pause very closely around toward dusk. So the hot particle boundary is there, and it's very close to the position of the plasma pause. There's a recent set of measurements by Mauck and McElwain on ATS-5 where they have plotted the position of, in this case it's called a low energy plasma boundary that's intersected by ATS-5. They've plotted its position as a function of Kp and as a function of local time, and using, by putting these two sets together, are able to get generally the shape and the position of this boundary as ATS intersects it each day as a function of Kp and local time. And the two lines there show the boundary for Kp of 2 and for Kp of 5. And this is really very close to what the plasma pause looks like. There's a sort of a bulge region on it. It goes to higher L shells in the afternoon, and it moves in like the plasma pause does for higher Kps. There are also measurements that David Winningham will talk about from ISIS that actually look at the low altitude signature of the inner edge of the plasma sheet ring current type region. But it seems that the outer part of the plasmasphere is bathed by a layer of hot plasma, which is then going to have an effect on what the convection field looks like. And the calculations of Jaggi and Wolf, this is just one of their particular calculations. They started with the ion sheet way back in the tail, turned on the convection field and let it gradient curvature drift in and convect in to a new position. This is 7 hours after the thing initially started drifting. But more than likely, the time scales we'd be working with are where it would drift from, say, L of 8 into L of 4 or something like that, shorter time scales. But the alphane layer here, or the hot particle layer, is this double dashed line around. And the effect what happens is when the hot particles come in, you get field-aligned currents, which then set up an electric field which alters the effect of the convection field inside the layer. And the effect here is that inside of the double dashed line, you've got predominantly co-rotation. The electric field, after this situation reaches a reasonable steady state, you've got a co-rotation type setup. Outside of that, you have very large fields. And across this boundary, there's a very sharp gradient in the electric field because of the effects of the very sharp inner edge and the field-aligned currents. The sharpness of the boundary is dependent on what the inner edge of the plasma sheet looks like, which is not that well known, and also what the distribution of the field-aligned currents looks like. This has an infinitely sharp boundary there. The gradient in the electric field will depend on what the inner edge of the plasma sheet looks like. But the nice thing about what this model shows you is that it enables you to get very large gradients in the electric field, which do not exist in a regular teardrop situation. So if you go from inside, you've got almost co-rotation. You go outside, you've got very large westward flows in the dusk sector. Past the split where it goes westward here and eastward here, if you inside you have roughly co-rotation, outside you have a larger electric eastward drift. Okay, there is evidence, sparse, but there is evidence for this sort of thing. This is electric field pattern developed by McElwain based on KP1 type situations from ATS-5. This would be a case where ATS-5 is probably inside, most of the time, inside of this inner edge. And he finds no westward drift at all. There is a slight bulge here indicating that some of the convection field on the average is penetrated because it causes the particles to drift out to higher L shells, but there's no strong westward drift. He only sees westward drift when there's an injection, a very high injection of substorm type particles. But this would be a case where ATS is probably inside that boundary, and in this case the fields are very low. It's mostly co-rotation with just a little bit of bulge on it. There's an example on the Chattanooga data. This is also a very quiet day where the Chattanooga facility at L of 5.6 is also probably continually inside this boundary. And this is the north-south field. Well, it's both north and east field, but it would correspond to the magnitudes here would correspond to westward drift, the pluses. And the general effect is that there's no field there at all. Very, very small. The Chattanooga facility in this case is probably inside the inner edge. It does not see the convection field. There's very little penetration. Now, there is some evidence that as you go across that inner edge, you do see a jump in the electric field. This is a case of Don Garnett's from Engine 5 where he's been talking about generally the relation of the measured electric field with inverted V's. But if we look down here, here's the plasma sheet, here's the inner edge of the plasma sheet. You can see there's a jump of about 50 millivolts per meter in the electric field at the inner edge of the plasma sheet. It's higher outside, or as you go on into the plasma sheet, it drops away to nothing inside the plasma sheet. This may well be an example of shielding by the plasma sheet of the earthward part of the convection field. Okay, what does this mean then in terms of the cold particles? Here are drifts at Chattanooga on an active day when Chattanooga probably crosses back and forth across this boundary. We don't have, in this case, correlative data of where the plasma sheet location is, so some of this is maybe wishful thinking. But generally, on the drifts in the afternoon sector, this is UT, so you need to subtract 10 hours. But in the afternoon sector, you go from a very low drift where you're inside the inner edge into a region where generally you get a very strong westward drift. This probably is an example of millivolts per meter. There's 20, 40, 60, 80. So you get a strong westward drift. This is a northward field, but a westward drift. And then you're continually outside the region measuring the strong fields. You cross the discontinuity where you go from the eastward flow to the westward flow at about 2200 local time. And then you're in an eastward drifting region until you get back around past dawn, and you're probably back inside the inner edge of the sheet again. This could be then an example of again, high fields outside the inner edge, lower fields inside. And in terms of the cold plasma then, can we turn that one around? So it would have a very interesting effect on detaching plasma and on what the cold plasma drift does. Before the enhancement of the convection field, you'd have a quiet plasma sphere with a hot plasma layer out here. We'll just worry about this particular sector right now. At the onset of activity with a rapid enhancement of the convection field will penetrate initially to the inner regions. It takes a while to develop the current systems to actually shield it off. It initially will penetrate and will give you a smaller teardrop size where you start getting co-rotation here and drift off in this direction, which probably begins to develop a tail or a detached region. Then at the same time, however, you're going to inject hot plasma to lower altitudes, which is then going to gradient drift around, the protons will, and will establish this layer at a much lower altitude, like this. Now we have a sharp boundary, at least spatial boundary in the electric field, that has moved to a much lower altitude, earthward of the old boundary. Outside of that boundary, you would have rapid westward drift. Inside of that, you would have roughly co-rotation, and across that boundary there should be some reasonably sharp spatial gradient in the electric field, at least if the Chattanooga data is an example, and also the engine type data. And so that, and in this case, you would get a detachment because of this very steep gradient in the electric field. It's no longer a smooth effect like the teardrop, but a very sharp jump. And what you begin to find is then that the size of the plasmasphere is determined not necessarily by the size of the teardrop as much as how far is the convection, how far is the inner edge of the plasma sheet able to penetrate, because it is at that point that the plasma is torn off. And it's then the degree of penetration of the inner edge of the plasma sheet which determines where the plasma pause is located on each rotation. Subsequent compressions and expansions can still take place, but the actual tearing off of plasma would then be controlled by the hot plasma as opposed to just the convection field without the hot plasma. And this then has an impact on the dynamics of how fast the plasmasphere can change shapes and sizes, because it's now determined by how rapidly can this boundary come in, which may be more on the order of drift times of the particles when they're injected here and when it can cut around, and how rapidly can the currents be set up to actually cause the shielding. And this is something that I would really like to, I think will be discussed more in the convection section and also the hot-cold particle section. Let me just end with a couple of questions. What are the time scales involved in this shielding effect? If it works, how long does it take? the calculations where you start with the ion sheet way back take a long time, 7 or 8 hours to reach a steady state, and that's not going to do you much good in this case. But it may be shorter time scales. I think we need to look at that. What's the real? Let's try to get a measure of the sharpness of the change in the electric field across the inner edge of the plasma sheet. We need to do some correlative stuff between Chattanooga measurements and, say, ISIS measurements of the inner edge to see if there's really a jump in the electric field across the inner edge of the plasma sheet. Why do the Chattanooga data disagree with the ATS data, which largely sees, ATS largely sees co-rotation. Chattanooga sees very large fields. Is there, and whereas Chattanooga is at a lower L shell than ATS, is it because there's a reasonably large inflation of the magnetic field during these times that caused Chattanooga to actually sample farther out in the equatorial plane? Is this boundary between hot and cold plasma a heating boundary? McElwain has suggested that the ring current, the hot particles at the inner edge of the ring current may just be old plasmasphere particles that got heated up. Keith Cole talked about that also a long time ago. Maybe there's processes like that go on. And finally, we need to really get at the detailed nature of this boundary from a self-consistent point of view, where you drive the hot particles in, allow the cold particles to dump the hot particles, but at the same time allow the hot particles to shield the cold particles and adjust their drift, so that you come out with the real detailed picture of what detaching plasma and plasmasphere size changes are. Thank you.
One question of clarification. Is that boundary that you call I guess their plasma sheet boundary, whatever, is that hashed region?
Yeah.
Do you identify that with the equator edge of the soft roll zone or not?
In the dusk midnight to dusk sector, I would equate that with the inner edge of the ring current. It's predominantly protons. Past midnight, it would be generally, at least according to the equatorial measurements, would be the inner edge of the electron part of the plasma sheet.
I see it's more complicated than I wanted to get into. So
okay,
you did raise a lot of questions. You can see we got a lot of questions, and we got an awful lot of papers too. And I wish we'd have more time.
Yeah, we'll have more time in later sessions because of our confusion this morning.